Today we're going to look at the rocket equation, and we're going to do that in the context of this problem. So we have a model rocket with a total mass of 200 grams at launch. Of the total mass, 25 grams is fuel. The exhaust gases leave the nozzle at constant mass flow rate and at a speed of 800 meters per second. The rocket burns for 1.5 seconds. Neglecting air resistance and assuming the rocket travels straight up, what is the velocity of the rocket when the fuel burns out? So this is a classic application of the so-called rocket equation. Now the place that we're going to get the rocket equation from is conservation of linear momentum. So we're going to apply conservation of linear momentum to this problem, and the rocket equation will come out of that equation. So we're going to start off just with a little sketch here to get a coordinate system and a control volume established. So there's our rocket just taking off. Exhaust gases coming out the bottom there at 800 meters per second. So I'm going to establish a coordinate system, and everything's moving in one direction here. So we're just going to let x be the coordinate, x equals 0 on the ground, positive x pointing straight up. And of course, g, acceleration due to gravity, is in the opposite direction to our x. Also want to establish our control volume, because we're going to apply control volume momentum balance to this. So the control volume will enclose the entire rocket and cut right across that exit. So that's our control volume that we're applying this equation to. Now a couple of important things about that. First of all, our coordinate system is fixed to the ground. It has to be an inertial coordinate system in order to apply conservation of linear momentum in the equation that I've got here. The control volume, however, is moving with the rocket. So it's accelerating away from the ground with the rocket. It's attached to the rocket. And so we'll be dealing with that as we simplify our equation. So the next thing we need to do is apply conservation of linear momentum to that control volume. So we're going to talk about all of the terms in here, decide which ones we need to keep, and how we can represent them in a simplified form to apply to this problem. All right? So the very first term we see over here is the weight of everything in the control volume. Remember, these 4 terms on the left-hand side of the equation are all the forces acting on the control volume. So the first one is the weight. Well, we certainly need to keep that here. This control volume has some mass, and that weight is an important part of conservation of momentum in this direction. So we're going to keep that term for sure. We'll see how to simplify it as we go forward, but we're certainly going to keep it. The next 2 terms here, the pressure distribution around our control surface and the viscous force term, we're going to neglect. We're going to neglect those because in the problem statement we were told to neglect aerodynamic drag. And aerodynamic drag in a situation like this is basically those 2 terms. The pressure distribution on the surface of our control volume and any viscous shear stresses on the surface of our control volume. That's what aerodynamic drag is, so we're neglecting it. So both the pressure distribution and the viscous term here are going to disappear. So we can get rid of our viscous term and we can get rid of our pressure term. Now the last term on the left-hand side here is our reaction force, and our control surface doesn't cut through any solid objects, all right? So that reaction force there we can also get rid of. So the only force acting on our control volume is the weight of everything in the control volume. Moving over to the other side of the equation, the first term is the unsteady term. So this is the rate of change with respect to time of the momentum of everything in the control volume. And so we definitely need to keep that, because at the beginning this thing doesn't have any momentum, and at the end it certainly does have some momentum. So just based on that alone, we need to keep the unsteady term because the momentum is changing with time. So we certainly need to keep that. The last term in the equation has to do with the momentum flux across the control surface. And we certainly have momentum leaving our control volume down here at the bottom at the exit. but we're going to assume that that's a single uniform exit. So when we rewrite this term in the equation, we're going to use the uniform flow assumption for that. All right? So before we rewrite that equation, I just want to establish some other notation over here. We already have our g vector written here, but I want to write down g in our coordinate system. So the g vector for our problem is the magnitude of g. That will be 9.81 when we substitute numbers in, but it is in the minus I hat direction. X is pointing up, g is pointing down, so minus I hat direction. I'm going to define the velocity of this rocket just as v. Okay? So as we work forward here, v is going to refer to the velocity of the rocket. So the velocity of the rocket has some magnitude, which we're interested in, and it is in the I hat direction, positive I hat direction. Last thing I'm going to define over here is the velocity of these exit gases. So coming out of the bottom here, the exit gases have some velocity, which I'm going to call VE. And we'll represent VE also by a magnitude, VE, but those are going to be in the minus I hat direction, because the exit gases are in the negative x direction, all right? Now, when we rewrite this equation, we're going to talk lots about this, but the velocity of those exit gases we need to get relative to a stationary observer on the ground. This VE that was given in the problem, 800 meters per second, is relative to the rocket. So we'll need to deal with that when we rewrite our equation, all right? Now notice that everything is in the I hat direction, either I hat or negative I hat. So when I rewrite this equation, it is a vector equation as it stands right now. I'm just going to extract just the I hat component, right? So I'm not going to have I hat in each of the terms. We're going to extract just the I hat component, because that's all there is an I hat component. So when we do that, our body force term here is just minus mg. So that's the weight of everything in the control volume. It's mass times acceleration due to gravity, and it's in the negative I hat direction. Now realize this mass is a variable, right? It's decreasing as time progresses. As the rocket moves up, mass is decreasing. So that's a variable, but it represents the force due to the weight at any instant in time. And that's the only force we have on the left-hand side of the equation. So now we go over to the unsteady term, the rate of change of momentum. So we need to keep that derivative for sure. But everything in this control volume is moving with the same velocity. So the rocket housing, the unburned fuel inside, the parachute if it's in there, fins on the rocket, all of those things, they're all traveling up at a constant velocity, or at the same velocity. It's not constant. So this v can come outside of the integral, and all this is the rate of change with respect to time of the mass times that velocity. So that's the rate of change with respect to time, the momentum of everything in the control volume. And realize both of those things are changing with time. Mass is going down and the velocity is going up, all right? The very last term here is the momentum flux across the control surface. And remember, that's happening at this exit. We're going to assume uniform flow here. So we can just represent that by the mass flow rate at the exit. It's positive because it's an exit. It's positive in the uniform flow version of the equation. So that's the mass flow rate. But now we need to get this v right here in the coordinate system, okay? So remember that minus VE is the velocity of the exit gases relative to the rocket itself. But to get that velocity relative to a stationary observer, we have to add the velocity of the rocket onto that. So we have the force, just due to gravity, is the rate of change of momentum in our control volume, and then this is the rate at which momentum is leaving the control volume. So that's our simplified version of conservation of linear momentum. Now what I'm going to do next is just break this one term up using the product rule. So we still have minus mg on the left-hand side, but here we have m dv dt plus v dm dt. And then I'm also going to distribute this mass flow rate into these two terms. So here I'll have m dot v minus m dot v of the exit gases, right? So that's conservation of linear momentum. And we need to set that equation aside for a moment. We're going to come back to it in a minute. And we need to consider conservation of mass. So we've considered conservation of linear momentum. We also need to take a look at conservation of mass. So we'll just write down our conservation of mass equation. So this is in its most general form. So we can make the same assumptions to this equation as we did to our linear momentum equation. It's certainly an unsteady problem, but realize that this triple integral of rho dv is just the mass. So this term is just dm dt. And then we still have just a single uniform exit, and its mass flow rate is m dot. So that's what conservation of mass tells us. And just to write this a little bit differently, dm dt is minus m dot. So the rate of change of the mass in the control volume is minus m dot being the rate at which it's leaving. So that certainly makes sense. Now, take a look at this equation, which is conservation of mass, and take a look at these two terms in our conservation of linear momentum equation. So if we take this dm dt and replace it with minus m dot, realize these two terms cancel each other. So including conservation of mass and combining it with conservation of linear momentum, we greatly simplify our conservation of linear momentum equation. So we just have the weight, m dv dt, and then minus m dot ve remaining. So we're going to clean up this equation, continue to work with it, and solve for the velocity when the fuel burns out. So the next thing we're going to do is take a closer look at this dv dt term. I'm going to represent dv dt in a little bit different way using the chain rule. So dv dt can be written as dv dm times dm dt. So using the chain rule, those two things are equivalent. Now remember, when we looked at conservation of mass, we found that dm dt is minus m dot. So I can write this as minus m dot dv dm. All right? So I'm going to take this dv dt and replace it with minus m dot dv dm. And we'll see what we can do with that. So we have our m and our m dot, negative in front of that, now times dv dm. And we still have m dot ve here coming from there. All right? Now, if you take a look at this equation, the only two things in it that are changing as this rocket moves is the mass and the velocity. So we only have two variables in here. Everything else is constant. The g is constant, the m dot is constant, and the ve is constant. So we can separate variables. So I'm going to start by just isolating dv dm all by itself on the left-hand side. So when I do that, I get mg minus m dot ve all divided by m dot and m. All right? So I've got dv dm is equal to that. Next thing I'm going to do here is just make it so v is the only variable on the left-hand side. So we have g over m dot. Notice the m's cancel. And we have minus ve over m. Notice the m dots cancel. All right? And that's all times dm. So now we're ready to integrate this. So we integrate both sides. So the integral of dv is just v. On the right-hand side, remember we're integrating with respect to m, right? So we're integrating with respect to m. So this will be just gm over m dot. And this will be minus ve times the log of m plus a constant of integration. All right? So g m over m dot minus VE log of m plus a constant. Now, in order to solve for the constant of integration, we need to know the velocity at one particular time. So this thing is starting off from rest. So v equals 0 when the mass is equal to the initial mass. So we have 0 on the left-hand side because our velocity is 0 at the beginning. We have g over m dot times the initial mass, m naught. And then we have minus VE times the log of m naught plus a constant. So that's when we put in our initial conditions. 0 for velocity and m naught for the initial mass. So realize that m naught is the 200 grams we were given in the problem. So solving for this constant, the constant is just going to be VE ln m0 minus g m naught over m dot. And now that we have our constant of integration, we can go and write our final expression. So the velocity is going to be g over m dot, m minus m naught. So remember, m is the variable over here. M naught and m dot and g are all constants. And then the other term, we have our exit velocity, log of our mass over m naught. So that's our final expression that allows us to calculate the velocity when the fuel burns out. So all we need to do to get that number is put in the mass when the fuel burns out. And that'll be 175 grams, right? Because there's 200 grams to begin with, 25 grams is fuel, so 175 grams is the final mass. So the other thing we need here is our mass flow rate. But remember, we have 25 grams of fuel, so 0.025 kilograms. And that fuel burns in 1.5 seconds. So our mass flow rate we can just get from that mass of the fuel and the time, and that works out to 0.016 repeating, and that is kilograms per second. All right? So now we have everything that we need to put into this equation. So we'll do that. So our velocity, g, is 9.81 meters per second squared. Mass flow rate we just found, 0.016 repeating, kilograms per second. Now, you have to be careful here. M minus m naught, so that's the final mass minus the initial, realize that's going to be a negative number because the final mass is smaller. And that's going to be our 25 grams again. But it'll be negative 0.025 kilograms. We put it in here. So that's our m minus m naught. Then I'll come down here. VE, that's our 800 meters per second. Velocity of the exit gases. And times the log. Now here we have a ratio of masses, so I'm just going to put them in grams. So our final mass is 175, and our initial mass was 200. And those are both in grams. So notice, because it's a ratio of two masses, as long as I have them in the same units, it doesn't matter what those units are. So I didn't really have to convert them to kilograms. So all of this gives a velocity of 92.110 meters per second. So the velocity of this rocket, when the fuel burns out, is going to be 92.1 meters per second. So the only thing we have left to do here is write our concluding statement, and then I'm also going to list the assumptions that we made along the way. I haven't been listing them as I go because I don't really have the real estate to do that, but we'll list those all now. So our concluding statement is, so the velocity of the rocket when the fuel burns out is 92.1 meters per second. So the assumptions we made along the way if we just think back to when we went through the linear momentum equation, first assumption we made there was no aerodynamic drag. So remember, no aerodynamic drag eliminated the pressure and the viscous force term on the left-hand side of the momentum equation. We also said that there's uniform flow at the exit. So this is a uniform exit. And it had constant mass flow rate. The mass flow rate was constant. Also, acceleration due to gravity is constant. We just left that as a constant, 9.81. So g is constant. And the other assumption we made is that everything happened in the x direction. In other words, the rocket traveled straight up. And those are the assumptions we made along the way. So our final answer, 92.1 meters per second, is how fast this will be traveling when the fuel burns out. So I hope you found this useful. Thank you very much for watching. If you have questions or comments, please put them below. Thank you very much.